So I'm Rich Brueckner from Inside HPC. You might know me from that, with the guy with the red hat. Been in this industry a long time. But big data, if you haven't noticed on this show floor, just about every booth is talking about big data. I think I saw a guy with the vacuum cleaner from Freeman. He had a big data shirt on. I wish I got a picture of it today. So this is absolutely what's going on. And sorry about this. Yeah, okay. So I'm just going to present a few slides, then I'm going to introduce my panel. So I did a presentation once in Taiwan, and they said the proper way to introduce yourself to an audience is to first to tell them that you're not worthy. And looking at the stellar panel I have here, I go, that's blatantly obvious. But the second thing you do is tell a joke. So I'm going to skip that part. This is my publication about big data. And unlike HPC, the target here is, it's for the enterprise. And when we talk about big data, I want to make something clear here. Big data is a relative term. Your big data from your site might be very small compared to someone else. And in this case, for tonight's purposes, this is a term that IDC spent 6 months coming up with, okay, and getting agreement. Big data equals high performance data analysis. The big data people in the Hadoop space, what you've been reading about in the papers, when you say HPC to these guys, they don't identify with that. They might have a bigger cluster than you have at some of these labs, but they say, that isn't us. We don't do that. So they came up with this, and high performance data analysis is really what we're here today to talk about. So these are two worlds, and what's that book? Men are from Mars, women are from Venus, and there are a lot of commonalities. And what I'm seeing, talking to the people in the booths this week, is that there's a lot to learn on both sides as these worlds converge. And I think companies like Dell are the ones to watch as this matures. So I'm an old-time marketing guy, and I always like a call to action. If, you know, we all read about big data all the time, and there's a lot of different definitions out there, read this book, Big Data, A Revolution, by, well, the one author is Kirkier. So this is the best thing. I learned more about this. I was writing about big data for 2 years, and I learned more from spending an afternoon with this book than I did in that 2-year time. So with that, I'm going to introduce our panel here, and we've got a very interesting microphone setup, and I'm going to have you guys introduce yourselves, because you probably can hear each other better. So there you go. Why don't you pass that down and tell us who you are and where you work.
I'm William Law. I'm from Stanford University, and I work for the Stanford Research Computing Center. And just so everybody can see, these are two microphones taped together. So hopefully you can hear us in stereo.
Hi, I'm Scott Yockel. I'm from the University of North Texas. That's like in the Dallas-Fort Worth area. I'm the manager of high-performance computing on campus.
I'm Scott Nolin. I'm the head of the technical computing group at the Space Science and Engineering Center at the University of Wisconsin-Madison.
I'm Erik Deumens with the University of Florida, Director for Research Computing.
Boyd Wilson, Software CTO at Clemson University, and also work in lots of other areas with analytics and big data and HPC.
Okay, so Boyd, since you've got the microphone, please come over here, and we're going to have, each panelist is going to give us a few slides, about 5 minutes apiece, on what they're up to with big data, and please hold questions until the end.
Anyway, so let me quickly, I've got a few minutes to go through, kind of give you an outline of our storage environment, our big data types of things we're doing. And there's kind of the outline of where we're going. Palmetto Storage is our main cluster. That's our cluster. It's a condominium model we use for researchers. We provide a little bit of infrastructure for them. They pay for the nodes, and we collaborate, you know, on all those.
Even closer.
Even closer.
Yes.
Okay. So there's 1,900 nodes, almost 23,000 cores, almost a million CUDA cores, and then we have 300. In the last benchmark, we did 396 teraflops. That was just with the newest nodes, because the other one slowed it down. We have another 120 teraflops additional, not benchmark, as part of that. Like I said, the condominium model. Home storage is done on SAM-QSF and Scratch, and some big data type things are done with OrangeFS. I'll get to that in a second. Here's kind of the diagram we have, where we have our Scratch cluster actually separates two different network topologies. We have FDRIB and then 10 gig MX. And then we also have our SAM-QFS, which was for the home and archive. And there's kind of the numbers for that. So kind of one of the things we're looking at doing in the future is taking 32 Dell R720s, 520 terabytes of scratch, just kind of growing it out, and enabling user access via WebDAV so people can mount Scratch from their desktop to get their data up there. We're also doing Hadoop over OrangeFS with MyHadoop as part of the cluster. So you can launch MapReduce jobs as part of your normal workloads in the HPC cluster so the students and everyone else can get experience with that. And there's kind of, and the Science DMZ actually connects back to the 100 gig innovation platform over I2. So just kind of some things we're doing that are interesting. We have some tests we've done with the file system across the 100 gig innovation platform. We got 37 gigabits per second writes with just a few nodes. We had 12 storage nodes and 8 clients being able to produce that throughput. We also did some persona tests just to kind of test things. We got 70 gigabits per second. We're doing a similar thing on the floor here between Clemson, USC, I2, and Omnibond, and we're able to get some tests, and I saw some numbers. We're getting up to 70 gigabits per second performance. So just kind of showing some wide area capabilities. The collective cluster is our real data aggregation cluster. The first thing we're aggregating is social media data from GNIP. We're pulling it in real time, pushing it into Elasticsearch. Also have Hadoop on the nodes. OrangeFS is underneath that. Researchers use WebDAV to access it from their clients. And we're also doing D3 visualizations. It's an open source project we're starting called Social Tap, where you can actually go in and do real-time visualizations of the social media as it comes in. So there's kind of some numbers on performance numbers on those 16 servers talked about, up to 12 gigabytes per second. And there's some MapReduce numbers that we're doing. But the interesting thing we have here is you see OrangeFS and HDFS kind of are similar in the middle. If you see OrangeFS remote at the top, this kind of blew us away. And we actually got a 25% performance increase by putting OrangeFS remotely from the MapReduce jobs. And we totally weren't expecting that. And then we did some research, and it was because of local discontention between HDFS or OrangeFS and the local working. So it's kind of an interesting little science project there. Yep. And then we also tried some scaling out, where you actually take 16 storage nodes and tried scaling out to 32 and 64 MapReduce nodes, and we actually got some nice scaling by keeping the storage nodes similar. So some interesting performance numbers. And that's just kind of a network diagram of how we're connecting all the various different things. You kind of saw it at a higher level. I just wanted it there available in the slides for people.
So the point I want to make is more general rather than the description of what we have at the University of Florida. I want to sort of point out the context and draw a little parallel between what is happening in the big data space now and what we have seen in the past decades with high-performance computing. In high-performance computing, we've seen the element or the evolution from serial computing to shared memory, parallel computing, and then MPI parallel to now massively parallel with GPUs. And there's an analogy that I want to draw with big data. We started by having local file systems where people create data and they want to analyze it. Then we went to shared parallel file systems so that you could have more processing work on the same data. Then we have Hadoop distributed file system where the MapReduce algorithm takes local data and then you have to sort of have a shuffle phase, and then so that's where it becomes more like MPI, message processing, and you have to coordinate the distribution. And now we are talking to really worldwide or nationwide where people create repositories and they want to do searches with all the data from possibly geographically located different locations. And again, we will have to create workflows that will do certain processing, but sort of synchronize those workflows with the data flows that will be necessary to make sure that the data is at the right place at the right time to do the work you want to do. And I make this little table here to show this parallel. You have a programming control, serial, tightly coupled, loosely coupled programming or direction of your work. And here is the high-performance computing thing that we saw over the last several decades. And this is what we've been seeing really come to fruition in the last 5 to 10 years. You go from single processors with point-to-point, which is very analogous to people analyzing large files, possibly, and Dropbox-style collaborations where one researcher takes some data, uploads it to Dropbox, somebody else takes it down, makes a change, puts it back. And then here you have the tightly coupled programming, where you have shared memory multiprocessors, and you know that in order to really do shared memory programming, you have to put locks on your data structure so that only one process is making a change at one time. And here we have the same thing. When you have across a site, for instance, multiple clusters or a single cluster, a parallel file system, the data coherence is a main challenge of making a parallel file system work. And then we go to loosely coupled. You have distributed memory clusters where you have to do computation, send messages, analyze the message, send something back. And here we have the same thing with MapReduce, people creating worldwide workflows and using tools like Globus Online that do asynchronous motion. So that was my little introduction for the panel.
Thank you, Erik. Scott, you're up.
Okay, I'm Scott Nolin, and here you have a picture of the Space Science and Engineering Center. Our primary mission is, this is our building. It's a tall building with a lot of antenna on top, you see. Here you have a view from our rooftop of Madison, and we're in an isthmus between two lakes. And I think it's a nice picture from our rooftop. Data and remote sensing is really what we're all about. I won't go into the real details, but this just covers our major initiatives, and atmospheric research really is the prime factor, especially with satellite data. And so what shapes our storage solutions really has to do with how we're built as a group. We're a research center. We contain many groups and projects. Often they have different funding sources, and though we're in the same domain. The technical computing group I work with, we provide an infrastructure to share and combine these resources in a way that's more powerful than they would be able to do on their own. And atmospheric research via satellite meteorology is our major focus, as I said, and it has large data needs. Now, one factor of it is a large majority of our work is fairly large file sizes, 100 megabyte files, so that will shape a lot of times the type of solutions that we pick. In some ways, that's very advantageous for certain types of file system. Most research is not strictly operational, so high availability is not required, but data integrity is critical because in some cases we're building a satellite record, which may be a backup for a national archive or that sort of thing, and it's critical that our data has a high level of integrity. If you have never dealt with data corruption, in my opinion, you haven't dealt with large amounts of data, even moderately large amounts of data over time. Here's just an overview of how we do things. We basically use very uniform components, but have various solutions. The reason we do this is we want to be able to work with something that a project might want to buy for a small use case, like 40 terabytes or whatever, where they might have a NAS. But we also need to work with larger file systems. So we have a Lustre file system, which is about 1.5 petabytes. We have Lustre file systems, and finally have Lustre with ZFS on the back end for some of our disk archive stuff. And so one thing that's emerged for us is what we call our high-performance storage infrastructure. And the key components of that for us are InfiniBand as the fabric, basically, for it. Really, once we had to take the step to using InfiniBand for our MPI jobs for numerical weather prediction, which is something else we do, not just satellite remote sensing. Once you've done that, it's really hard to spend more money for Ethernet and worse latency and lower bandwidth. So once that's there, and because it is a little different, and you have different hardware to do it and different cabling, it's easy to exploit this now for our data infrastructure. Lustre router is another feature that's we're using. This allows us to provide our large data volumes to any network that we have in the building. Patchless Lustre clients is another, seems like a small thing, but that really made a huge difference for providing these file systems to any Linux system in the building. And there's some beta work we're doing on aggregating the various file systems into a single file system that exported to Windows desktops and whatnot. This is using extended attributes of files to make essentially make a metadata type thing where it's just a pointer that you update periodically. But that is, there's a group in the center working on that, and I won't speak to that much because it's really in beta, but it's pretty interesting work for things like our researchers. While you often need to access this data at high performance, sometimes you just want to be able to pick and choose files and do visualizations or do things on a much, much smaller scale than you would think about for high performance computing. but the value to the research can be very high to have it in whatever form they want. And that's all I have. So,
Okay, thank you, Scott.
All right, so my slant on my talk is a little bit different than the general technical talk. As far as solving the data deluge at University of North Texas, it's mainly talking about how much growth there has been. Oh, it doesn't change up here. This is just a little basic. Most people probably aren't aware of University of North Texas because you always hear of UT, you always hear of Texas A&M. Then there's other large universities in Texas like us that are like 36,000 students. We have a huge amount of research that's going on. One of the top computational chemistry and electronic structure programs. Anyways. And so since I have been there for 3 years now, we've had a tremendous amount of growth on campus using high-performance computing. As you can see here, we arrange against a number of different departments. We have people in the College of Education now doing high-performance computing. We have people in kinesiology that I've met with doing high-performance computing. So you were starting to see it in areas that you wouldn't see it before. And so because of that, we have a wide array of different types of data needs. So people like in computational chemistry are writing huge integral matrix files that are terabytes at a piece, huge single files upon these numerical calculations. You have material science who is writing a lot of information to files. They're generating tons and tons of data that they will then want to visualize later. So, and then you have people like bioinformatics and other teams where they're generating tons and tons of tiny little files at a time. So you can see that's a wide range of different type of utilization. And as you can see from this last part, we anticipate this kind of growth to continue, if not, to accelerate even past what we've seen in the past 4 years, mainly because of big data. And so we just deployed a new system just a couple months ago. We finally finished all this, and this is all the partners of the system. And our basic setup is a huge increase in computing power with, this is the kind of thing that's nice to show the people paying the bills, that with only 42% increase in your cost, you're getting all of these metrics from the previous 3 years. So our setup is 10 times more high-performance computing storage. This is with the Dell Terrace Gala HSS 4.5 solution with the new 4 terabyte nearline SAS setup, and also on Lustre 2.1. This is just kind of regular setup. This is a bit new for us. As you'll notice, there's not just one central cluster that you're logging into in one place for the administrative. For the user, there's multiple different types of situations you can log in from the internet. This provides us with a whole new level of complexity and a whole new feature-rich type of things that we weren't able to offer before. There's multiple different places that users can log in, like on the far left of your screen, that are a visualization login. So while they're running their code, if they want to visualize stuff on the fly, for instance, people who are doing climate modeling, they want to check to see visually what's going on along the way. They can do that, and they have the connection straight into the high-performance computing from that to do visualization on the fly like that. And so that's one new feature. As you can see from the yellow, these are all connected Mellanox FDR InfiniBand, and so this 56 gigabit is what allows us to have the performance in order to do the type of storage requirements for reads and writes that we need. And in addition to that, we have to have some type of middleware storage or middle performance storage that's not for runtime data. And so we have a SAN that's used for this. And the way this is also set up, because it's just a NFS space, you can mount this anywhere, right? This is actually nice because this was an existing SAN that we had previously. We were able to migrate from one cluster to another cluster, allowing users to keep their same research storage space. This is also available to experimentalists to dump data on that can then be ingested into the high-performance computing. So it's a really nice, flexible way to have storage. You have storage in your home space, you have storage that's on the SAN space, and you have high-performance storage. So having this kind of flexibility has enabled us to have the kind of growth that we've had in computing. So then we have the standard setup from the DT solution. With our initial testing with only 80 clients, we were able to get 13 gigabyte reads and 8 gigabyte writes. The reason why we couldn't do more than that for clients is because we had to have half of the previous system running while we had half of the new system up and testing. And once we were that, we must, allow users to have access to the new system while we're tearing down the other half of the old system. Because we have the infrastructure of like in-row coolers and those types of things in the data center, you have to literally install and maintain 2 clusters in the same physical space. It's quite a logistical challenge. So,
Okay, so first off, we are a new center. And I really like this picture because it shows Stanford has a lot of really great existing computational history and resources. We're not trying to replace anything. We're simply trying to supplement and fill in the gaps. As you can see here, we're really just trying to fill in the dirt between the existing structures. Right now, our group has has 6 people, 3 system administrators, including myself, a director, and a strategist, and then a facilities person. So the tradition at Stanford is for each research cluster to be an island. Each system has stood alone and been on its own. I think inherently that creates all sorts of data issues. And an easy example is one of the first clusters we inherited used a single shelf of Panelist storage. It's a great high-performance file system, but if you just have a shelf, you don't really get any benefit at all from the parallel file system properties. And so hopefully we can get people to work together more and generate economies of scale and better systems over time. So the other issue historically has been backups. Every researcher does not want to pay for backups, but they do need them. They think they don't. Recently, within the past week, we had some bioinformatics folks. They were cleaning up their data. They have a 2 petabyte file system. They accidentally deleted 150 terabytes of data and had no backups. So this is the storage resources we use right now. As I said earlier, we have a very diverse set of clusters and systems and history. We'll start out with AFS. We have about 70 terabytes of AFS. Stanford has a long history of AFS. I think that there are more fans for AFS than anything I've ever heard at Stanford. And we have, and so that's led to a lot of usage across systems, and everybody, there's a tendency within certain departments to approach everything as an AFS solution. It's not high performance. It doesn't work very well for a lot of resources, and across research computing, we're moving away from using that. But there's a grand tradition. A recent expansion on campus has been to Box. We actually have 2 Box instances. One is for general use, and everybody gets 25 gigabytes of data. There are actually larger amounts of data available for individual research groups. And it's not normal high-performance data, but it's really handy for researchers to use to share their data. It's been really helpful, and I've been really surprised how quickly it's been used across campus, and simply because of the collaboration capabilities it enables. We're a large GPFS shop. We're mostly using that in the bioinformatics space. Right now we have about 2 to 3 petabytes of GPFS. So we're a big user. We're also a big Lustre user. Right now we have around 1.5 terabytes across 3 systems. Our large Lustre system should be expanding to probably 2 petabytes over the course of the year, or hopefully. We also use a variety of NFS appliances and services. It's sort of the bread and butter of our system, and we use a lot of custom appliances ranging from Isilon to a little bit of Panelist. I think it's slowly going away. And NetApp is heavily used across the enterprise space on campus. We haven't been using it that much in the HPC realm, but it's a very popular. We have a very strong historic relationship. The other issue that nobody's really talked about is if you have sufficiently large data, data transfer is a huge issue. And as I said earlier, we have a lot of separate clusters, and if you have lots of separate clusters, data transfer is a huge issue. Right now we're using Aspera, the suite, a bit on the bioinformatics side. It's a fantastic, very fast data transfer tool. Unfortunately, it's fairly expensive. We also use Globus Online, and that's a very robust wonderful tool. And then, as I mentioned earlier, big heavy users of Box.com. I did not put up here, but something I think is a dirty secret across research communities is there's heavy use of Dropbox for using and for transferring files. It's not something our information security office wants anybody to use, but it's a very popular solution, and it's something that we need to be aware of. Our concerns for the growth of storage and working with storage generally in the research realm, I think one of our biggest pain points right now, especially on the bioinformatics side, is simply IOPS. It's a huge challenge, and that's something we're coping with. And I think as more people use the large 4 terabyte nearline storage drives, it's just going to get worse, especially as densities increase. The other issue that everybody has is storage growth, and so many issues come out of that. Sharing transfer workflows is a huge issue. I mentioned some of the ways we're coping with that, but creating and submitting and running jobs, the workflow part of it is really challenging. Backups. Backups and data integrity are a huge issue. We don't yet know how we're going to cope with all of that, but we're working on it. The other issue is long-term data retention sustainability for various experiments. Once an experiment or research project winds down, that data, it's very useful and very important to retain, but nobody has the current ability to really pay for it. How do we handle that? We don't know. We're trying to cope with that. Security and compliance on the PHI and HIPAA side is a huge challenge. We just started working with that, and we're coming to terms with it. I'd love to talk to anybody about what they're doing in that space. And then, of course, cost. So the path forward, we hope to standardize across platforms, use more open protocols for access. I actually hope to have fewer platforms sometime. We'll see how that goes. Everybody sort of has their own pet thing. And we'd like to provide common access via a variety of protocols like Lustre routers and NFS gateways to our storage protocols across campus. And I guess that's it.
Oh, thank you, William. Great job. Okay, folks, we're going to go to the Q&A section of the panel. And if I could ask the panelists, if you're going to answer a question, please repeat the question so that the camera can hear it. So let's just start with you. Who's got a question for our panelists today? Oh, come on. All right. Well, I got one. How many of you are using Lustre? I'm just curious. Wow. Okay. And maybe if we could go around, why is Lustre important to what you're doing?
I think the biggest reason initially is just large storage and having a single file system. People are really used to using POSIX type things, and it's a great solution. I also work historically with a lot of engineering clients, and they go and run on larger national systems, and so it's nice to have the same file system across. They're already used to it.
Okay.
Yeah, for us, the Lustre setup is because the aggregated bandwidth you get with all the different OSTs, and we just need that kind of access to read writes at that rate. Not an incredible, like we don't need 40 or 50 gigabytes per second. Like in the 10 range is probably what the system is normally runs at. So. And
then Lustre's able to deliver that without putting up a sweat, I would imagine.
Yeah, it's not. And now that we're also, I would say now that we're in Lustre like 2.0, it's much more stable and much easier for us, and no more late nights. We hope we used to have 1.6, and if a failover happened from one OSS to the other, and you tried to revive it, and at that time we also didn't have a redundant MDS, we'd almost inevitably roulette wheel of will the MDS kernel panic,
Right.
So that's the kind of the joy of being past that in some newer technology.
Thank you, Scott.
We used Lustre initially for the main reason was just performance requirement for our large numerical weather prediction computer S4, and then once we had gotten into it, we actually benchmarked Gluster with the G also for that same project, and we couldn't get the RDMA performance out of it that we needed. So we do have a large version of both, but as we've worked more with Lustre, we're using it for things that don't have as high performance needs because the model works well, and it is stable. We've had good experience with it, and so and the ability to export it to patchless Linux clients of any type is what's really begun to make it more popular rapidly. So that's what.
Now down to Erik.
We're using Lustre mainly for performance. That was our initial, and then also because it's open source, so that we don't have complicated license fees. That was important.
Okay. Well, I'll keep the microphone, Erik, because I have one for you. Do you use Dropbox in your university as well? Is this a common thing? And Box?
No. There's an official statement that you're not allowed to use Dropbox, but
Really?
90% of our faculty do use it, but we're not allowed to use it. But we are actively building an infrastructure that will provide that feature with data that will be approved by the security office and make the privacy office happy. So we are working on a solution. We know it's real, but we know that the policy cannot be enforced until you have an alternative. You can't say, you cannot use that, and then they ask, well, what am I supposed to use?
Yeah.
And if you don't have an answer, that's not good.
That's not good. Scott has something to add, I think. From here?
Yeah, so at the University of North Texas, they had to go through a IT governance decision and go through legal with that, and they came up with the idea that if it's going to be used in the same regards that you would send an attachment to someone, and this was not something that was dealt with grades or any kind of like health type of information or any financial information, you could use Dropbox on.
It's I use it. It's an incredibly versatile tool. I mean, I can see why people want to use it in things like Box. But I can tell you that Dell is one of the corporations that blocks it within their firewall. No one can see. If you put something on Dropbox, they can't see it. Like a graphic, a presentation. Just so you know.
Well, we are moving toward, because we have, I think it's called SkyDrive or whatever the new Microsoft. Yeah, that is what we're moving to eliminate the Dropbox situation, mainly because from an administrative type of, I don't deal with it in high-performance computing, but from the administrative side of it, there's no control of the data. If the graduate student leaves, that data they have in Dropbox, their professor has no way to get it. So with inside of the Microsoft setup, we will have those kinds of ways to deal with that. So.
Okay, well, does anyone, we got a couple questions here. Go ahead, James. Okay, the question was about InfiniBand and which flavor are you using, and are you doing things like Rocky? So who wants to start? Who's the InfiniBand users in the group?
We have,
all of you?
I think we all are. But, I mean, we have we have FDR InfiniBand. We don't do anything special with it besides, the standard use of it.
Yeah. And you're on the latest generation then? FDR?
Yeah, FDR.
Okay.
We also have FDR. As I said, we have a variety of systems. And so to go to your first question, we use InfiniBand because we really need low latency for many applications. I think that we might be able to get away with something like iWarp, or a low latency Ethernet. And I'm very interested in that. For some of our applications, we actually do need the bandwidth of FDR. We have, right now, I have 3 generations of InfiniBand, so DDR, QDR, and FDR, ranging in clusters from clusters that are 1-to-1 non-blocking to 2-to-1 non-blocking, depending on the generation. So,
was there another question in the audience? Could you hand him the microphone? I think that's the way to do it. Yeah.
This one's not for Scott because I work with him. Yeah. But several of you have mentioned routing your Lustre mounts. And it sounds like if you can just mount your Lustre everywhere, just put Lustre on all your clients and mount it everywhere, it might solve some problems. Is there any reason not to do that anybody's run into?
Reasons not to do Lustre everywhere. Yeah.
Yeah, we currently don't do that, but we're interested in that because we have a visualization center that's not a part of the high-performance computing, because high-performance computing sits in the central data center, which is a security-restricted area, so only a couple of people can get in there at a time. The visualization wall, of course, needs to be where everybody can come to it, and so it'd be nice to do that and have that set up. We just haven't done it yet, mainly because the visualization center used to be at a different physical campus, and now we're all going to be in the one physical office space.
Yeah.
So.
Yeah. Any other questions from the audience? Oh, yeah. Please hand him the microphone.
All right. Thank you. Now, the Library of Congress is interested in very long-term archival storage of many things. They're trying to digitize many media so the paper doesn't rot and won't be available. So they're interested in things that might last for hundreds of years. When you're looking at your backups, are you worried about things on that type of timescale, or data wrap is looking at for keeping things for 5 years, 10 years?
Yeah. What's the timescale you guys need to keep things?
Well, we have a backups are for a working set that we keep for a certain amount of time because it's a backup, not an archive. We do have some data which is archived. We used to be a national archive for satellite data because the founder of our center put the first weather satellite into space or helped develop the instrument. That was his idea. So we were the national archive. We no longer are. Now we're a backup archive, but we follow the same procedures. And being a backup archive is what's freed us to now use whatever technology we want because there's regulation. So yes, they are concerned about it. And the way we look at it, or I know the way the data center that does that archive looks at this data is an archive is an active thing when it's electronic. So you have to have procedures in place to continually move its media over the years. You don't put it on a tape and be done. And you have to worry about integrity and all kinds of things. So.
Anyone else have a comment? Okay. Okay. Any other questions from the audience? All right, guys. Well, I want us to do one quick round. What's your biggest pain point now with data? Is it corruption, whatever? What would you say? And if you don't have one, you don't have to speak up. So I'll start with you, Erik.
The biggest pain point right now is to provide the security to the people who really need it, like HIPAA compliant or ITAR, EAR, all those things to make sure that all the regulatory audiences and auditors are happy.
Yeah.
Because there has been an increase in the last year of scrutiny and incidents that have resulted in bad actions.
Yes, and HIPAA compliance is a big issue in the enterprise as well. So go ahead.
Yeah, so I actually concur with security. That's one of the big things. And the second thing is just access, ease of access to the user so they can get stuff in and out. The reason that they go to Dropbox is because it's easy. So we need to make it easier for people.
Sure. Thank you.
I would say for us now it's mostly we're in a phase where we need to connect with the researchers and getting them to use the data and understand things they can do to have impact on their research. And so the security is important because we do sometimes deal with ITAR sensitive data, but not in a large data set. We try to publish defensively because once it's published, it's public. So, but that is an issue.
Once it's out there.
Yeah. We're kind of lucky because we don't deal with any kind of secure data, and I also don't have to worry about any kind of Dropbox situations. I'm just solely HPC. Yeah. I think the biggest challenge for us is educating users about their data. So previously in the past, a lot of computational algorithms, you generate lots of the data along the way, a lot of that scratch data that you don't necessarily need. Yeah. There's a lot of programs that automatically remove that. There's a lot of new users who write code, or we have a lot of bioinformatics users who generate lots of data and their codes don't do this, and it's educating them that you don't necessarily need all the raw data from all the different points. You need the beginning stuff, the middle stuff, and the end. You don't need all the steps in between necessarily because you can regenerate that data in a few days. You don't necessarily need to keep 5 terabytes per user per research project. So that's data management in that regard.
So as part of that education, Scott, I mean, I heard somebody saying, well, these guys will put 400,000 files in one directory, right? And just to run LS takes like 5 minutes or something. You have to deal with that as well, that kind of thing?
Well, yeah, just that, and then their understanding of where the file is located physically makes a difference. Mm-hmm. Even though it might look to them like it's all in one directory. Understanding how it's linked together, if it's local, if it's remote, if it's on high performance, the access times. Yeah. And so we consistently have to go through. You generally end up finding a group of users that you need to educate, and we go to their research group meetings that they would have and stuff like that and try to educate them a little bit. Yeah. It takes some time from us, but it also gives us a lot more less headaches down the road.
Right. You can provide better service for them if they help you out a little bit. Okay. William?
I think our biggest concern right now is security and compliance, so really the HIPAA. Yeah. And then the other thing that is huge, and it ties into that really, our backups and long-term data retention and archival things. We're not ready even to talk about long-term archival. I think actually we'll need stuff. I'd love to be in a position where we could worry about 100 years, but I think right now we're, worried about mistakes and catastrophic data recovery.
Yeah.
So.
Okay. Well, are there any more questions from the audience? I think we should wrap up here. Can we give our panelists a hand? I think they did a great job. Good job, guys.